Hello, and welcome to this video where we're going to discuss the dissolution process. To begin, I'd like to remind you of a couple of ideas. The first one is that you can have solutions in any form. So for example, it's possible to have solids dissolved in other solids. In fact, we call those alloys, right? Different metal mixtures, for example, are solid-solid solutions. It's also possible to have gas-gas solutions. The air you're breathing right now is a mixture of different gases all dissolved into one another. Most of what we think of when we think of solutions, of course, are liquids mixed with other liquids and liquids mixed with solids. Also, we'll talk a little bit about gases mixed with liquids, which you're also familiar with, right? Every time you open a can of pop, for example. But one thing that they all have in common is some basic terminology. And those two terms, of course, which you've heard before, are the idea of a solvent, which is just the substance present in larger amount. And what do I mean by larger? Greater than 50%. And in amount, we'll talk about how to do concentrations later. The second thing that we want to think about is the solute, right? The substance that's present in the smaller amount, of course. And of course, when we think about forming a solution, we have to think about the solute and solvent being separate from each other at the beginning. So the example I'm going to use, we'll go ahead and call the solvent the benzene molecule, which, if you remember how skeletal structures work, has 6 carbons and they're all bound together in a ring. And there are 3 double bonds that alternate, and there are hydrogens that are sticking out from each of these little vertices here. So benzene looks like that, a ring of 6 carbons with hydrogen sticking out. We'll go ahead and make our solute for this example the toluene molecule, which turns out to be very similar. It's still got the ring of 6 carbons, and it's still got little hydrogens sticking out in 5 of those places on the rings. The only difference is that in one position you have a carbon with 3 hydrogens sticking out, and I'll go ahead and make a little bit more space so that I can show you that hydrogen. Right, and again, this is our solute. It's called toluene. And our solvent is called benzene. These both exist as liquids, and so you could imagine a beaker full of benzene with its little rings. You could also imagine a beaker full of toluene and its little rings with the extra little carbon sticking out. But these are very similar molecules. And if we did a very quick review of looking at these molecules, we'd notice that they're what we call nonpolar, right? This is a nonpolar molecule. It's all carbons and hydrogens. And so is this one. And if we thought about the intermolecular forces then, the intermolecular force that we're dealing with is London, or remember the other name is dispersion forces. And just the same over on the toluene side. But when we mix those two things together, we put some of the benzenes in and some of the toluenes in, you have to imagine that 2 things are happening, right? The first one is we have to use energy, and I'll use E for energy. Why? Because we're overcoming solute, or solvent, IMF, right? Those benzenes have to be broken apart from one another. They have to be forced to spread out in my solution. Similarly, the toluenes have to be forced to spread out so that they're now distributed, right? A solution doesn't just concentrate all the benzenes in one corner and a toluene in the other. They're dispersed homogeneously within one another, so they're just all randomly dispersed. And to do that costs the energy of overcoming the interactions. However, what we get on the flip side is we get the release of energy. Why? Because we get new solute solvent interactions. And as long as 1 equals 2 or 1 is less than 2, right? I get more energy out than I put in, or I get the same amount of energy out that I put in, then we could say that dissolution is a spontaneous process. It happens without any external help. I don't need any help to put benzene and toluene together. All I have to do is pour them in the same beaker and they will dissolve spontaneously. Why? It turns out in this case it's because 1 equals 2. The same amount of energy that's used to overcome splitting the molecules apart from each other is the same amount of energy that's released when they form their new intermolecular interactions. And that's what we come to with the idea of 2 different types of solutions going forward. And those 2 different types of solutions are what we call ideal and non-ideal, and it all comes down to the intermolecular forces. Remember how I told you in the previous little bit that benzene and toluene, right? Benzene was the ring of 6 carbons with all hydrogens, and toluene was the ring of 6 carbons with the extra CH3 group coming up. That these were dispersion and these were dispersion, right? So this is solvent, solvent, and solute, solute is also dispersion. And when we put the 2 things together, also dispersion. So what I can go ahead and say is the forces are the same, and there is a bit of fudge here in terms of the strength of them, but we'll leave that out and I can fix that with you if you take PChem with me in a couple of years. But together they are also dispersion, and so an ideal solution ends up being the same types of intermolecular forces. On the other hand, let's look at 2 molecules that don't work that way. Water, which you'll remember its intermolecular force is hydrogen bonding, right? That's its pure force. And then acetone. Remember, acetone has carbons on either end. Remember, these are C with 3 hydrogens. And then there's a double bonded oxygen in the middle. These are certainly both polar molecules, but acetone doesn't have the right kind of hydrogens to hydrogen bond to itself. So acetone in its pure, the best that it can do is dipole, dipole. You notice that those are 2 different forces, and so together, water actually has the ability to hydrogen bond with acetone, right? This oxygen on the acetone molecule can hydrogen bond with water, and so together they can H bond. But you notice that the interactions that they do in the pure are different, and so there's a different thing that happens when they mix. And so we would say that that's a non-ideal solution. Now, what I need you to understand is that the key word here is still solution, right? They mix, right? So they've mixed before this, it's just that the type of mixing leads to 2 different things. The next thing that we need to point out is that there's a difference between the types of solutes and solvents in terms of the number of particles that form. And so let's take a look at that now. So another thing we need to think about in the dissolution process is not just whether it's an ideal or a non-ideal process and who's the solute and who's the solvent, but we also need to think about numbers of particles. And the question you need to be thinking about here is, well, what is the type of solute? And so we can break that down and we can talk about whether we're talking about ionic compounds or covalent compounds. And let's start with covalent compounds. And so for the example, let's go back to acetone in water. And what do we know about acetone? We know it's a covalent compound, right? There's no ions. It doesn't form ions in water. And so if I were just to draw little balls of acetone, right? We know that there's a liquid form in water that before we could say that there's N acetone particles. Afterwards, there's the same number, right? Because no ions form. And so in water, you know, I drew 5 over here. There's still the same 5. They're just distributed differently because there's now these little water molecules that are all around them. So after N acetone particles. If I put 5 acetone particles in, I get 5 acetone particles out. That is not what's going to happen with an ionic compound. So we'll use as our example for ionic sodium chloride in water. And what I want to remind you of is that ionic compounds generally come as solids. And so we could, for example, imagine sodium chloride. And I want to remind you that this is sodium plus and chloride minus. And also thinking to our periodic properties, sodium plus is going to be small, right? And chloride minus, because it took on an extra ion or an extra electron, is going to be big. And so we've got this structure of ions, and they're in this big solid lattice, right? So before, lattice of Na plus and Cl minus. What happens afterward, right, when I make my solution, is that we break up. I've got 1, 2, 3, 4 sodium pluses. And afterwards I've got 4 chlorides, but they're all separate from each other and there's still water molecules hanging around, right? After NX ions. Right here, I know that I get 2 ions for every NaCl that breaks up, but I could think of other examples. So again, a sodium chloride would make a sodium plus and a sodium minus, but we could think about a sodium sulfate making 2 sodiums and a sulfate, right? So there's 3 particles that come out of this. And so make sure that you're counting particles so that you don't get stuck later on some of the things that we're going to need to do. Think about ions, think about how many things that form when I have an ionic compound. The last thing that I want to think about with the dissolution process is to remind ourselves that there are ways to adjust solubility. You already know this. You're aware that if you're, say, working in a kitchen and you want to get more sugar into your water, what are you going to do? You're going to heat it up. And so one factor that affects solubility is temperature. And why? Because there's more energy, right? Temperature is related to the kinetic energy of particles. Particles at low temperature have less kinetic energy. They're moving more slowly. Particles at high temperature, of course, have more kinetic energy. And so what that means in a solution is that for gases in liquid, they are less soluble as temperature increases. Why? Because if I have a gas in a liquid, and I'm just going to draw little bubbles, if I heat up the temperature, all it's going to do is escape. And that means that it's not part of the solution anymore. Gases already had a lot of kinetic energy. Heating it up just gives them a little more, and they would much rather not be part of the solution, so they're going to leave. On the other hand, liquid in liquid, or solid in liquid, etc., they become more soluble as temperature's up. Again, you're used to this idea that if I want to get more sugar into my water, let's say that I can manage to get like 5 or 6 sugar molecules in at a low temperature, heating it up means that I can fit more. Why? Because there's more energy to overcome solute interactions. More sugar can break up because the temperature provides the energy to break those molecules apart from one another. And that's why that we get that thing that we're used to, that most things become more soluble as temperature increases. It's just gases that are the oddball. The next factor that adjusts solubility that we should think about is the idea of pressure. And remember, different phases, right? We've got solid phase, we've got liquid phase, we've got gas phase. Different phases respond differently to pressure than others. Solids do not care about what the pressure is. If the pressure is high or if the pressure is low, they take the same shape, they do the same thing. Liquids care very little. Again, just like solids, they have kind of a small range of shapes that they can do. It's gases for which pressure matters, right? Gases, the space that they take up, as we're going to talk about very soon, the space that they take up is defined by the pressure. And so gases become more soluble as pressure increases. Why? Because they're forcing the gas to take up less space, and if the gas takes up less space, then more gas can also come in. Again, you're familiar with this. This is what happens when you carbonate a beverage, that they put in that carbon dioxide under very high pressure so that it's stuck there. When you open that can of pop and you hear the hissing noise, that's because you just reduced the pressure. By taking away that pressure, the gas can now escape, and you would leave your solution there, your pop out for a while, it goes flat. Why? Because the pressure is lower and the solute escapes. There's one more factor that we definitely want to think about, and this one actually affects whether a solution will form in the first place. And then once we know it'll form, it also affects the amounts that we can get in. And that's the miscibility of two substances. And this is usually liquid with other liquid. And it's directly related to IMF, to intermolecular forces. So this actually brings us full circle to what we talked about back at the beginning. Things that have compatible intermolecular forces tend to have high solubility. So benzene and toluene, again, both with their dispersion forces, are compatible with one another. They like each other. This is going to be high solubility. Benzene is very soluble in toluene. Toluene is very soluble in benzene. On the other hand, water and acetone, right? Hydrogen bond, dipole-dipole, right? These are both based on the idea of polarity. These are probably pretty soluble with one another. Lastly, let's think about benzene and water. Not compatible, right? They are incompatible. Dispersion does not like hydrogen bonding. Low solubility. In fact, you can barely dissolve any water in benzene. Most of what you get is layers in your container. There would be one layer of benzene on the top, and there would be one layer of water on the bottom. But when intermolecular forces are incompatible, again, that's what you get. You either get layers because they don't mix at all and don't form a solution, or the solutions that form are very, very, very poor in the solute. So those are the factors you want to think about. You want to think about compatibility, you want to think about pressure, you want to think about temperature, and then have these mental pictures in your head of, oh, what are the particles doing? Are they breaking up? Are they forming more particles? Are they just staying as single units like a covalent compound would?